Tell us, O muse of those curious voyagers who traveled far and wide.
Into the depths of the quantum world.
Many realms did they visit, of manners and customs unacquainted.
And time and again, they could not perceive the vastness.
The depth.
And so, guided they were by Sapienza, the spirit of wisdom, casting light upon these worlds.
But lo!
Though she could illuminate, only the discoverers could enlighten.
But who, oh who these discoverers?
Sages. Quantum sages.
Real life physicists here on, Zoom.
And now, fellow sojourners, come ye with us on this quantum voyage. Accompany our explorers, Tara and Akash.
But hark!
The quantum world is one most fragile.
The act of observation itself can drastically alter its state.
And the manner in which you observe can change its outcome.
So, sojourners, we invite you.
With all else unraveling in the state of the world.
Immerse yourself into the quantum world that you are made of.
Observe with an indulgent, loving eye. And
Just be
present
present
in
in
the
the
now.
now.
Nothing to be observed.
See?
Well, what do you mean, see?
What does it mean to see?
No, I mean, what do you see?
See?
I don't see anything. All of Tara's foo-foo stuff. What in the world?
We are light.
Radiation.
Perhaps particles.
Perhaps waves.
Waves or particles, which is it?
Perhaps both.
But I don't see.
Depends on how you see.
But what does it mean to see?
What does it mean to see?
Whoa.
Whoa.
Do you see what I see?
I am Sapienza.
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 You are Tara and Akash.
Yeah.
How do you know our names?
Do you like to travel?
Yeah.
Yeah, how do you know our names?
Do you like to meet new people?
Yeah.
Like who?
Sages.
Sages. What are sages?
This travel of which you speak, I mean...
Are you adventurous?
Will it be safe?
Will it be dangerous?
Light. The alluring elusive. The alpha and omega of creation. Light that poured out when existence came into being.
Oh, wow.
Okay, hey, Tara, I'm not so sure we should be taking trips with strangers.
When do we leave?
Oh, come on, Tara, can't we just take a nap? Oh, could be such a lovely nap. To sleep.
Oh, to awaken. Light. I like light. But really, what is light?
And the journey begins. Our first quantum sage, Professor Yizhuang Yu.
What's the nature of light? A puzzle that lasted for centuries. It dates back to ancient Greeks, when science has sprouted fertile. Pythagoras postulates that light is a steady stream of particles, while Aristotle considers light as tidal waves in the ocean. These two opposing ideas sow the hidden tension of war. Through the mist of Middle Ages came the age of discovery. The first wave-particle war broke out in the physics community. Both sides tried to explain the laws of reflection and refraction. They resulted in opposite predictions, about the speed of light. However, light travels fast and its speed is hard to measure. Experiments at that time could not resolve the dispute. The war ceased for a century, waiting for new evidence to come. History enters a new era, the modern industrial age. Advances in technology led to new discoveries in science. Interference patterns appear as light passes through thin slits, and bright diffraction spots emerge in the darkness of shadows. These light spots are like tides in the sea that rise and fall. The particle theory can do nothing but suffer from defeat. The wave theory won gloriously the second wave particle war. It declares light as a wave in the electromagnetic field. Peace has only been maintained for less than 20 years. The concept of light quantum resurrected the particle theory. The third wave particle war had gone beyond the scope of light. The battle spread to all particles that had been discovered in nature. A peace treaty was finally made. Its name is called quantum. All matters are wave particle due. The same applies to light. Wave and particle live in peace under the quantum theory. Another century has passed. There should be no more war.
Sapienza,
Yes, Tara?
so does light travel fast?
Yes, Tara, faster than anything else.
Sapienza,
Yes, Akash?
are there miniature creatures like us in the quantum world?
No, Akash. The quantum world looks nothing like what you know, but you're composed of it.
Sapienza,
Sapienza,
Rest your minds. Light, the alluring elusive, sometimes a wave, sometimes corpuscular bundles of energy, sometimes here or there, sometimes here and there. The glue holding matter together. Light, the quintessential quantum. Quantum, it is the ancient world where curiosity leads to uncertainty. Light, the constant voyager, the messenger, peripatetic, bouncing, tunneling through, unstoppable, except in death, absorbed into being.
the photon has to die so that we can know of it and we can see?
it's not easy to see.
You have gotten a taste, and now I will take you to a feast of the strangest innards of quantum. To be or not to be, that is the question. Correction. To be and not to be. That is the, Man kann auch ganz burlesque Falle konstruieren. One can even set up ridiculous cases. Eine Katze wird in einer Stallkammer gesperrt, zusammen mit folgender Maschine. A cat is penned up in a steel chamber along with the following device, die man gegen direkten Zugriff der Katze sichern muss, which must be secured against direct interference by the cat. In einem Geigerschen Seelord befindet sich eine winzige Menge radioaktiver Substanz. In a Geiger counter, there is a tiny bit of radioactive substance. So wenig, so small, dass im Lauf einer Stunde vielleicht eines von den Atomen zerfällt. That perhaps in the course of 1 hour, the atom decays. Ebenso wahrscheinlich aber auch keines. But also, with equal probability, perhaps none. Geschieht es, so spricht das Zählrohr an unbeteiligt über ein Relais ein Hämmerchen, das ein Kurbchen mit Blutsäure zertrümmert. If it happens, the counter tube discharges and through a relay releases a hammer which shatters a small flask of hydrocyanic acid. Hat man dieses ganze System eine Stunde lang sich selbst überlassen, so wird man sich sagen, dass die Katze noch lebt. Wenn inzwischen kein Atom zerfallen ist, der erste Atomzerfall würde sie vergiftet haben. If one has left this entire system to itself for an hour, one would say the cat still lives if meanwhile no atom has decayed. Die Psi-Funktion des ganzen Systems würde das so zum Ausdruck bringen, dass in ihr die lebende und die tote Katze. The psi function of this entire system would express this by having in it both the living and the dead cat. A Spaufau. Pardon the expression. Zu gleichen Teilen gemischt oder verschmiert sind. Mixed or smeared out in equal parts. Die gegenwärtige Situation in der Quantenmechanik. The present situation in quantum mechanics, really.
Could you repeat that, please?
Welcher Teil mein klein Krummschnapper? Which part, my little crumb snatchers?
All of it.
All of it?
Let's try this instead.
You know how in that game, Clue?
Yeah, the one with that manila envelope?
Yeah, and all those murderers.
So, at the beginning, you don't know.
Yeah, you don't know who it is.
Anyone could be the culprit.
The possibilities are mixed.
Or smeared out in equal parts.
Yeah. I read that somewhere.
Quantum clue. At a birthday party, there is a tiny bit of evil, so small, and yet in the course of 1 hour, it bites one of the guests enough to commit the most heinous of acts. But also, with equal probability, any one of the other illustrious guests could have been bitten by this bug of evil.
Is this a fun party?
Shh.
The consequence, the unfortunate and untimely demise of Dr. Geiger.
Round
one. Classical clue.
Miss Scarlet in the bathroom with a wrench.
Colonel Mustard in the kitchen with the dagger.
Mrs. Peacock in the cellar with a revolver.
Mr. Green in the lavatory with a candlestick.
I gotcha!
Wait. Okay, wait. How did you know that?
Now, therein is the real question. The nature of reality.
What about me?
Perhaps, until we observe it, all guests are probable fiends, except, of course, the poor, unfortunate Dr. Geiger. Every single guest, until the point of observation, carries the potentia of the bug of evil.
Round
two.
Copenhagen clue.
Miss Scarlet in the study with a wrench.
Mrs. Peacock in the cellar with a revolver.
Mr. Green in the hall with a knife.
Colonel Mustard in the dining room with the lead pipe.
All possibilities are mixed or smeared out in equal parts.
Like in a game of musical chairs. Reality comes into being only when the game is observed and the music stops.
Ladies and gentlemen, I have followed a string of observations and concluded beyond a reasonable doubt that it is indeed Colonel Mustard who performed the heinous act in the dining room with a lead pipe.
So it's at this point that all the morbid possibilities, mixed or smeared out in equal parts, that we collapse onto Professor Plum being the true killer.
I beg to differ. I would like to think the killer existed all long before Detective Irwin's observations.
Oh, my little crumb snatchers. Reality, it could be way worse. All possibilities could be smeared out in equal parts, and that is the reality.
No way.
Yes way.
And so, we begin again.
Round 3, multiverse clue.
Ein, zwei, drei.
Colonel
This is
Mustard,
what
have
the
you
Voyager
observatory
right
and
back.
the revolver?
And so, they all exist at once. Nothing collapses. All possible scenarios are real, each in an actual universe of its own. In one, Mr. Green. In another, Mrs. Peacock. In another, Colonel Mustard. In another, Mrs. White. And perhaps, in yet another, Dr. Geiger sprains his foot and never shows up to the party, little knowing how fortunate they are.
That's efficient.
That makes my blood boil.
And Schrodinger's poor cat. What happened to her?
Same thing. In the first round, it is mixed or smeared out in equal possibility of being dead or alive until the detective opens the diabolical device and the state of the cat collapses into being either dead or alive upon observation.
And in the second round, in one universe, we could observe it being dead, and in another, equally real, being alive.
And in yet another, it could have tunneled out of the device altogether and disappeared. And that's only 2 rounds.
Well, which one describes reality?
Which one describes reality?
These rules may not be complete. We may be missing a whole other set.
What? So quantum mechanics isn't complete? Well, what is all of this for?
Oh, Detective Irwin should know.
Sorry, Crumstatchers. This is categorically beyond my jurisdiction.
Oh, please, 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 we need to understand.
Oh, my little crumb snatchers, I'm afraid this is beyond my jurisdiction as well. But I know someone. Professor Ken Intriligator. Oh, Professor!
The interpretation of quantum phenomena is indeed confusing. Copenhagen interpretation, many worlds. A great physicist advocated the shut up and calculate interpretation. We know the rules to do precise calculations, which fit precisely with observation. But there's still something so mysterious and bizarre about it, even to the professionals. Roll the dice and see what possibility is realized. Is poor Schrodinger's cat in the box alive? Well, in some outcome, the answer was no. Maybe there's another world where the answer was yes. These look like 2 cats, but it's actually a single entangled cat. There's a certain magic to quantum mechanics, provided you don't look too closely. The observer just can't be detached. Spooky entanglement is everywhere. We could try to harness entanglement, maybe use it for quantum computing, but it's ethereal and easily broken. The collapse of the wave function, hidden variables, observation says no. It's just non-commuting observables and good old entanglement. And everything, even us, we're made up of ripples of quantum fields, a dynamical soup that fills space and time. Some fields can Bose condense, as happens with the Higgs field, or in a superconductor. Using the technology of materials and lasers, The magic of quantum mechanics is being illuminated and applied on larger and larger scales. But it's not yet scaled up to the level of the mysterious cat kit. Shut up and calculate. Remember the Bose-Einstein condensate.
Oh, the quantum worlds.
The nature of reality remains elusive, and yet
Quantumness is omnipresent.
Germinating at the most minuscule realms.
Where even the smallest of quantum particles are strong in character.
two breeds there are, the hostile fermions and the friendly bosons.
And if perchance fortune be favorable,
come they together in harmony.
These bosons in a manner most extraordinary.
Forming a communal quantum state.
The Bose-Einstein condensate.
Bose-Einstein condensate.
Bose-Einstein condensate.
In the coldest spaces of the universe, when agitation from heat subsides and all quietens, a strange quantum state of matter can emerge, the Bose-Einstein condensate.
Where were these spaces?
Not far away in the cosmos, but right here on Earth. In pockets of near emptiness hover these quantum states, these condensates.
And what their composition?
Minuscule quantum specks, cooperative specks, colluding in concert, creating a common conglomerate.
Who the creators?
Why, humanity.
Us?
Us?
Why, yes. There are those who have unraveled the science and art of isolating atoms into the tiniest of spaces, cooling them to the lowest of temperatures, and bidding them to form the strangest states of matter.
Close encounters of the bosonic kind.
Hark! The tale of how the Bose-Einstein condensate comes to be. Oh, Smita, come ye! Professor Vishveshwara, do tell!
Here we are, my friends, at 300 degrees above absolute zero. Speaking of quantum condensates, not even outer space is cold enough for them, warmed to 3 degrees above zero by the cosmic light from the early universe. But back on Earth, cold atomic scientists, many, my friends, cast their wizardry on tabletops, enclosing a suspended gas of atoms in a glass case, sodium, potassium, or rubidium perhaps. Friendly atoms, bosons, which love to congregate, brought together to a clump by laser beams, photons pelting, slowing, and cooling their motion. Yet, not cold enough until the invocation of an everyday trick, evaporation. Like with a cup of coffee, except in an invisible bowl formed of magnetic fields. The faster atoms flying out helter-skelter. The remaining slow, and cold enough, just a millionth of a degree above zero for a quantum magic transition to happen. For each atom to fill space as a wave, each wave to overlap with the other, indistinguishable, together to act as one, move in harmony, free of friction, free of rotation, save for little whirlpools, quantum whirlpools. The quantum condensate, a new state of matter. To behold an image of this coldest conglomerate in the universe, we may turn off the invisible bowl, disperse the atoms, destroy the condensate, and in the act, capture its exquisite imprints on a camera. And then we may begin the magic all over again.
Moving.
Gliding.
Cruising.
Sliding.
Common conglomerate.
Common dance.
Flowing superfluid.
Unified quantum being.
Alas, coming down isn't pleasant. Or should I say, surfacing up.
What's happening?
Reality just hit. Ow! Brace yourself. The terrain here is horrifically rugged.
Where is here?
We're inside a raw material.
Oh, what?
Inside a solid. Inside a hunk of metal deep, deep down within its quantum recesses.
Oh, my vision's getting blurry!
What can I say? You're in a crystal lattice.
What?
A crystal lattice. And there's disorder, dissipation. Just keep walking. We need to navigate our way from one end to the other. I feel hot.
I'm being bombarded.
It's the electrons. They're everywhere, trying to get to the other end, just like us. Like us? Yes, they're hot too. They might get stuck in here, just like us.
What? Stuck? Oh, help! Help!
Oh, there's liquid everywhere! Hurry! Get to the plug! We're surrounded by the Fermi Sea! The what? The electrons! They formed a treacherous Fermi Sea!
A sea? Oh, but I can't swim! Oh, I just want to take a walk in the woods and then you show up and now I'm gonna die. Oh, I'm gonna die in this Fermi Sea! Oh,
Get to the plug! Gosh!
I just want to...
Gosh! Gosh! Get to the plug! Relax. All the same electrons, navigating their parent crystal lattice. Through the order, through the disorder. Relax. Relax.
Did you say a Fermi Sea?
Yes, we're surrounded by it.
We're inside the crystal.
Aluminum, perhaps?
Lead.
Aluminum.
Lead.
Aluminum!
Relax!
Well, whatever it is, it's a lattice of atoms.
Positively charged atoms. Arranged here and here and here and here.
And the electrons have formed this nebulous continuum, sweeping their way through.
By encountering impurities, defects.
And yet, somehow navigating their way through. But how does the Fermi Sea figure into all of this?
Oh, somebody help! Monica!
In metals, electrons are not confined to nuclei, but are instead free to move about the material, forming a Fermi sea. However, electrons are unfriendly creatures, called fermions, who refuse to all pile into the same state with the same energy. If we add electrons to build the sea one at a time, each would prefer to occupy a different energy state. The laziest electrons, which sit on the very lowest rung of the energy ladder, move the slowest. Each additional particle will occupy the next rung of the ladder, 1 quantum of energy away, each moving a little faster than the previous. Metals have a huge number of electrons, on the order of 10 to the 23, so the last few electrons will have an extremely high energy and move around the fastest. And it is these electrons that mainly account for conduction in materials. In a perfect world, the most energetic electrons would dash across the material in an organized fashion, like athletes sprinting on a track. But real materials are filled with defects, like on a rough, bumpy road. Electrons scatter off of these imperfections, a process that dissipates energy in the form of heat. This sounds complicated and chaotic. However, physicists can exert exquisite control over the way electrons behave, like a choreographer directing a group of dancers. Applying a magnetic field causes the electrons to start dancing in circular orbits. They waltz along the edge of a material in orbit-like trajectories, forming a one-way stream of current similar to traffic flow on a highway. Remarkably, these edge currents are impervious to scattering because they can't easily change directions and therefore transmit electricity exceptionally well. Alternatively, experimentalists can engineer the energy of electrons to be very small, even smaller than the Coulomb repulsions between particles. In this scenario, electrons start exhibiting many-body cooperative behavior, like a group of synchronized dancers all spinning in the same direction. Nevertheless, fermions will be fermions, and the electrons all do this while avoiding and repelling each other. Finally, on a more practical level, electric fields can be used to turn on and off the flow of electrons, a feature that forms the basis of modern computing.
Well, all be fermions stacking themselves one upon the other, together forming this Fermi sea.
The tumultuous, dangerous Fermi sea that nearly put an end to us.
This is all your fault.
My fault?
Well, yeah, the photons, the superpositions, the smearing out in equal parts.
It's fascinating. If you don't see that, then I don't know.
But then you go off and do the Bose-Einstein dance, and then all hell breaks loose.
Yeah, that was great.
But then we nearly drowned.
Yeah, not so great.
And then you slapped me?
I saved your life. You're welcome.
Oh, okay, well, here we are, trying to discover the nature of reality, and you're doing it all wrong. You think you could go off on these flights of fancy and cruise along with condensates?
And you, dear sir, think that discovery involves taking micro step after micro step, tearing things apart, fragmenting the whole? You can never understand the whole through its fragments.
Oh, well, you think that you can just discover reality in your bones, and you think that the song and dance that you do make up your delusional reality.
Well, you can't understand the whole through your nosy, systematic, analytic, excruciatingly dissectional methodology.
You have no method, just madness.
You have no madness, just method.
Oh, you'll spin everything into anything that just suits your...
You'll spin anything into everything that suits.
Oh, I cannot take this journey with you.
I cannot take this journey with you. It's finito. Done, done, done. Ah! I'd rather go alone. Stop! Sapienza, I need another plunk.
We are Planck quanta apart.
Oh, the world of fermions! I should have known. We're all fundamentally fermions. We can never coexist in the same state. Why did I bring them on this journey? There's no holding them together. So, is that all? Does it all end here? Is there nothing I can do to bring fermions together? Nothing to be done?
Back to our action-packed story in just a moment. But first, were you ever a child? Were there other children in your family? Did you ever experience what professional child psychologists call sibling rivalry? Did you ever incessantly flush the toilet when they were taking a shower? Did you ever precariously balance an open bag of flour on the upper ledge of their door so it would fall on them and make a tremendous mess when they'd enter their room? But enough about me. Look, whether we admit to these things or not, and being a quantum sage, I know who among you is guilty, it's quite common that siblings may experience what in professional psychological parlance are called issues with each other. They often try to avoid each other. Nevertheless, you can usually find them together around the table at dinner time. And why is this? It is because the strong positive attraction of a good home-cooked meal and the coercive powers of parents can overwhelm their natural mutual antipathy. Electrons in solids are like children in a very large, weird family. They're little brats running around all the time, trying to avoid each other because of their common negative charge. Like charges repel. They were each birthed by a neutral atom, which in parenthood became a positively charged ion. The ions attract the electrons, and on average, the system is neutral everywhere. But when one of the ions is displaced, local charge neutrality is temporarily violated, and there is a surplus of positive charge in the vicinity of the displaced ion. Like parents, the ions are big and slow and can only move around a little bit. But the electrons react to the displaced positive charge like kids respond to the dinner bell. In physics language, the slowly evolving ionic displacements, called phonons, are said to mediate an effective attractive interaction between the electrons. Now go give your sister a hug. We may push this analogy even further. In some families, parents may sit down for dinner and be joined by one of their children while another kid turns up somewhat later, after the first one is back up in their room wasting time on social media and the parents are away from the table watching Netflix or reading a book. Thus, the children show up in the same place, but not exactly at the same time. In physics language, this is what is called a time-retarded or delayed attractive interaction. Electrons in superconductors behave the same way. This delayed effective attraction further helps the electrons to overcome their natural instantaneous repulsion. The physics is, of course, quite a bit more complicated and involves quantum mechanics, Howley's exclusion principle, and a fair amount of mathematics. But the end result is that the effective attraction between electrons results in a state in which the electrons are paired. This special pairing state is what we call a superconductor. Superconductors exhibit an array of remarkable properties, including vanishing electrical resistance below a critical temperature, expulsion of magnetic fields, persistent electrical currents which flow without dissipation, and fascinating behavior at a junction between two superconductors known as the Josephson effect. The theory of superconductivity was developed by John Bardeen, Leon Cooper, and J. Robert Schrieffer in 1957. At the time, Bardeen was a professor at the University of Illinois at Urbana-Champaign. Cooper was his postdoc, and Schrieffer his PhD student. Their work forever changed physics and was one of the great triumphs of 20th century science.
And thus, perhaps no two fermions can be in the same quantum state. But then again, my crumb snatchers, you aren't in the same quantum states. Two fermions of opposite spins come together and pair. Two fermions of different orbital momenta come together and pair. Two fermions of entirely different dispositions come together and pair. Two fermions, one having flights of fancy, the other endowed with systematic methodology. Only in pairing can they enter new terrain. You can't go it alone.
Lo, they can be bound from afar, as electrons are within crystals, sensing the other's presence, roaming in resonance.
And why just one pair? Plentiful pairs could there be, as pairs no longer unfriendly, ready now to condense to form that communal quantum state.
Superconductivity! What becomes now of the Voyagers? Come they together to overcome strife, to find harmony?
Alas, fellow sojourners, these are uncertain times. and the constraints of time and space imposed upon us on the Zoom world compel our voyage to take pause.
We have seen glimmers from many a realm. There exists a soft glow endowed by the quantum world within each one of us, and it shall lead us through the shadows into effulgent light.